I heard sulfuric acid, so H2SO4. Another one? H, what? No, that's not an acid. What is that thing? That's a polyatomic ion, so that guy's out. How about that one? Carbonic acid. So anything that's got two H's that are going to pop off and not charged. So how's this lithium hydrogen carbonate going to change the pH of a solution? Going to decrease it? Nay, it will not decrease it. So I have a lithium hydrogen carbonate, and what's going to happen when this thing touches water? I'm sorry, did you say dissipate?
I don't know.
Somebody want to help that out? Disassociate, okay. All right, so is the lithium going to do anything to the pH? Why not? It's the cation of a strong base. It's a group 1 metal, and to do something, it would have to grab a hold of something. And will it grab a hold of anything? No, it doesn't want to associate itself with anything in water. But how about the hydrogen carbonate? What do you know about that anion?
It wants an H.
Why?
So,
It's the anion of a weak acid. Okay, so then if I throw my HCO3 here with a water molecule, I'm going to end up with carbonic acid and hydroxide. So what's the pH going to do? Yeah, more hydroxide, higher pH. Does anybody know what this is used for? What?
a med, I have no idea.
Yeah. What kind of medicine? Antidepressive, maybe antipsychotic. I don't know if it's used for antipsychotic, but possibly. Lithium carbonate, hydrogen carbonate.
It's kind of one of the last steps before.
Carbonate has to do with psychotics?
No, the lithium does. Yeah. That would be great if you could just, a couple scoops of baking soda and fix you right up. It'd be cheap. Okay, so what are we doing here? We got a buffer, 50 milliliters of 0.12 hydrobromic acid added to 500 milliliters of a buffer at pH 7 consisting of phenolphthalein and sodium phenolphthalein, 6.6, 0.1 and 1.26. Okay, so what should we do first with this? Find the number of moles of each of the things. So I've got a salt and a weak acid, and then the thing that's going to be added, which is going to be the hydrobromic acid. So I'll 1.2 mole per liter and 0.05 liters, and I've got 0.1 or 0.5 moles per liter and 0.5 liters, and I've got 1.26 moles per liter and 500 milliliters. So 0.25 moles of the acid, and then what do I get here? 0.63 moles of the anion, and then what do we got up here? 0.06 moles of what? Basically H plus. Why don't I say HBr? Because it's a strong acid and they're not going to be connected to each other. Okay, so then I'm going to set up a nice table. I have my weak acid of my buffer and the salt for my buffer. And then my initial is 0.25 and 0.63. And my change is going to be what? 0.06. So what is this hydrobromic acid going to react with? The anion. Well, one way to think about it is it's anion and cation. Okay, so they'll react. The other way is we added an acid, right? So is the acid part of the buffer going to react with it? No, the base part. So then I'm going to actually end up making 0.06 more acid and losing 0.06 of my base. And so then at equilibrium, I'm going to end up with 0.31 and 0.57. And then I need to calculate out my the pH now after this this change has occurred. So pH is equal to 6.6 plus log of 0.57 divided by 0.31. And do we have a pH there? 6.86? So 6.9? Did this change very much? Did the buffer do its job? Yep. How much do you think it would have changed pure water's pH? Probably 5 or 6 orders of magnitude. All right, so I have a citric acid sodium citrate buffer, and what's the initial pH of this buffer? Okay, so we can do that. pH is equal to, and what's the pKa for my acetic or citric acid? 3.14. Okay, so I got 0.25 up top and 0.62 down here. And what do we have for a pH for this buffer? 2.75. Okay. And I'm going to add hydrobromic acid. So what are we expecting the solution's pH to do? Go down, but not very much. Okay. So I need to calculate out moles for each of these things. So I've got 2 moles per liter, but I've only got 5 milliliters, so 0.005 liters. And so 0.01 moles of the acid. And I've got 0.62 moles per liter, and it looks like 0.755 liters, and 0.25 moles per liter, and 0.755 liters. Make sure that you calculate it out like this. Don't make a mistake with the volume. What mistake might be made? Don't add them up. Yeah, that's not this. We're not adding up the volume, because what we're trying to do is figure out how many moles, how many actual particles of weak acid and particles of salt are in there before I do the addition. Right? So this is not 760 milliliters. Somebody have a value here for this acid? This weak acid? And for the base? Okay, so then I've got my acid and I've got my salts, and my initial is 0.468 and 0.189, and my change is what? How? Add more acid. So add 0.01 here and subtract 0.01 here. And then at equilibrium, I'm going to end up with 0.478 and 0.199. Okay, and so then I just do the calculation again. So 3.14 plus log 0.199, 0.478, and my bad, 79. Okay, and what do you get for pH for this? What? 2.71? So did we get a very big change in pH? Did this orange go bad? No. Do you imagine that the pH of an orange is probably somewhere around a little less than 3? Can you imagine that the orange itself is a buffer? Why would the orange want to be its own buffer? So its acid doesn't do what? Destroy itself. So it's going to want to buffer at a particular pH. So it would want to have some sodium citrate in there to make sure that it didn't deteriorate its own fibrous structures inside. And you don't want to open up an orange and have it just be like mushy juice.
Make it simpler to eat.
No, make it simpler to drink.
I like orange juice.
All right. It's really bad for you, but whatever.